Well, my name's David Strain. I'm president of APS. It's a small systems development company in Canada specializing in reducing energy consumption in buildings through improving the control logic in their HVAC systems. We also work on a device which allows us to generate completely clean work with no pollution at all. The device is actually patented in the United States, in Europe, and in Canada. You can view the patents if you go to our website, apscontrols.ca, and go to the patent section. It'll provide links to the 3 patent offices. The patents are public domain now, so they can be used by anyone. And at the same website, if you go to the R&D section, in the hydraulic displacement motor section, there are several reports which explain exactly how this technology works. Now, the new advancement is based on a more efficient hydraulic actuator, which is allowing us to create the clean work. Now, this is a conventional piston here. This particular one is a pneumatic one, but it works in the same function as a hydraulic one. What happens is the fluid goes in through the port, and it drives over what they call a boundary face. It's the moving face area of the piston, which is connected to the shaft, so consequently the pressure times the area of the boundary face generates a force on the shaft. Now you see how this one will drive forward when I pressurize it. So what you're seeing there is the pressurized fluid drives the shaft forward, and if this, say, was 10 square inches inside here, then you'd have a situation where if you had 10 pounds per square inch coming in and 10 square inches of face, it'd be 10 times 10, be 100 pounds of force pushing on the shaft. Now there's another purpose that we use to use the pistons, allowing us to generate the invention we have. Now, a piston could be used to put pressure in and cause the shaft to drive to do work. But if you push back on the shaft against the pressurized fluid, what happens is you can use this actuator as a pump. So if I push back on it, see what happens there is I push the fluid out of this into the balloon. Now, if you displace the fluid from within the actuator, if it's a pressurized fluid, that pressurized fluid could be used in another device as its source of fluid. And that's a very important part with respect to the whole invention. Now we have 3 different types of actuators which have been patented. This first one here we're showing you is a diamond-shaped actuator. It was patented in 2002 under my name in the US, Europe, and Canada. Now you see it drive forward when we pressurize the actuator. So what's happening there is we have the hinges anchored here, hinge anchored here. We have a hinge here, and a hinge here, and a hinge here, allowing the device to expand as a diamond when it's pressurized. Now, what happens in the totalization of the force is all 4 walls exert a force. They all come together as one common force pushing up on the shaft. Now, we've tested it under a situation where we've allowed to compensate for the friction within it, and the best advantage we've ever seen with respect to the diamond is 26% advantage over conventional piston, meaning that for the same volume input into the diamond-shaped actuator as what goes into the conventional piston, we'd have a situation where the diamond would generate 26% more work. Now that's very important with respect to the operation of the machine. Now, the scientists and engineers who have tested this have reported an advantage of between 15 and 17% advantage. What they use as a start point is where they see it start to move, in which case the friction has been overcome. So that accounts for the difference between the 26% we've witnessed as a total force with respect to the 15 to 17% as a working force that they've witnessed. Now, the second type of actuator we have also a diamond-shaped actuator, but it's only a half diamond. Now we pressurize this. You watch as it drives forward, you see that there are only 2 moving walls generating force on this particular actuator. So what you have is a force on this wall and a force on that wall coming together as a common force pushing up on the shaft. Now, the force calculation for this using vector theorem would be the cosine of that angle times the area of the wall times the pressure times 2, because they're 2 walls, would predict the force capabilities of this actuator. That's been forwarded by several engineers and scientists to this point. Now what we've seen is not quite the result they predict with their calculation. If you use the calculation that they say would, at 10 degrees rotation at that angle, what we would have is 98% advantage over a conventional piston. We have not seen anything close to that with respect to that, so we're suspecting that the vector theorem does not really apply in this sense, in a practical sense. Okay, now we have another type of actuator. Watch as this one drives. You see, with this particular actuator, we have it's hinged and anchored to that point, and hinged and anchored to that point. It's hinged here, 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 and here, so that it's able to expand as you saw. Now it's a device that was actually patented in 1874. Now, it was by a man named Mr. Riley. It's quite an advancement with respect to improvement on efficiency in hydraulic actuators or any fluidic actuators. The second one you saw from the half diamond was actually a device very close to that. Was invented by Mr. Sleeper in 1903. The full diamond was actually invented by myself in 2002 or 1999. With this one here, what we have is the force that's being pushed on inside on the diaphragm generates a force on the top plate, but it also generates a force on this outside wall, pushing it out to straighten it up, and also pushes on this outside wall. So instead of having with a conventional piston, instead of having just the boundary face, pushing just the one face to create the force, this one has the one face, which would be the equivalent of what's in the conventional piston, plus it's got the 2 outside walls. So now we do have a little demonstration of a document here. It's what this is, a little practical consideration with respect to how forces accumulate in this kind of a situation. If you had a situation where there's a little man there, little man A, pushing up, and he's not capable of lifting the load in the table. He's pushing with force 1, and it's not enough force to push up. So he's got a red face, he just can't do it. And then what happens is 2 of his little friends see he's in trouble, they come under the table, and they push on the wall. So what happens is little man B pushes on that point and pushes this out till the legs straighten up. Little man C does the same. So what you have accumulating there is, instead of just little man A's force, force 1, you've got force 1 plus force 2 plus force 3. So the total forces are able to lift the table up, where the one force on it alone is not able to. Now, if we consider how that relates to the actuator, if you look at the top plate here, it's very similar to what little man A would be. It's a force. And then if you look at the side wall, that's very close to what little man B would be. It's pushing out this way, which is causing a force going upward here, and little man C is pushing out that way, which is causing a force upward. So in this particular application, you've got a situation where little man A, B, and C are all coming together as one common, more powerful force than just what the top force would be. Now, relating to the regular piston, if this is 10 square inches and you're driving with 10 pounds per square inch in it, it would be 10 times 10, be 100 pounds of force pushing on the shaft. If you put 10 psi into this actuator, Mr. Riley's actuator, and it's 10 square inches on the top, there'd be 100 pounds of force through his whole driving range, where there'd also be a force by little man B and little man C. So consequently, through the range, you would have 100 pounds of force plus this force, where through the same volume change, the regular piston would only have the equivalent of little man A, the 100 pounds of force. So if you look at the formula, work equals force times displacement, you'll have a situation where they're both driving the same distance, 10 inches and 10 inches. This one here has force of 100 pounds through 10 inches. This one here has the work being 100 pounds through 10 inches plus 2 more forces. So consequently, this actuator is more efficient than what a conventional piston would be. Now, we've got a demonstration for you, which will show the nose-to-nose change of a conventional piston and Mr. Riley's actuator pushing against each other. So that's Mr. Riley's actuator here. You see how the two hinges here are not touching the two outside posts. So we're starting off with Mr. Riley's slightly retracted. The top area of Mr. Riley's is actually more than 20% smaller than the area of the conventional piston. So there's a 20% deficit in work area with Mr. Riley's if only the top plate is the exerting force in Mr. Riley's actuator. If the two sidewalls are not helping him, the conventional piston has a 20%, more than a 20% advantage over Mr. Riley's. So if that were the case, and we pressurize them simultaneously to the same pressure, what should happen is the conventional piston should overpower Mr. Riley's actuator and push him back. And that he would be more powerful because he'd have the same pressure over a greater area, therefore more force. Now, when we do pressurize, I throw the switch, we'll exert both actuators to the same pressure. And we can see that the switch here is allowing pressure through, and these valves are open, so the pressure is going through and up through a tube to Mr. Riley's. The pressure is also going through here and up through a tube to this actuator. So they're exerting the same pressure to each. So if we watch the Mr. Riley's actuator where he's starting, and we will see, okay, so you saw very clearly that Mr. Riley's actuator overpowered the conventional piston. And you look at the two gauges, you see we're at about 6 psi each. So they're getting the same pressure, and Mr. Riley's actuator actually became more powerful than the conventional piston because he pushed the conventional piston back. Now, keeping in mind the demonstration we showed you with the balloon, when Mr. Riley's actuator pushes this piston backwards, the fluid that's in there would be pushed out of it. Consequently, we would be using it for another source if we want. Now, you have a situation where the top area of this, again, is 20% smaller than the area of the conventional piston. There's a formula in fluidics demonstrating work, and we talked about the work equals force times distance. There's also another formula which is work equals pressure times volume change. So what we have is a situation when, because this area is smaller by 20% than the regular piston, if you go from empty to full, and they drive the same distance on the Mr. Riley's actuator as the conventional piston because they're linked together, we would have a situation going from empty to full with Mr. Riley's, there'd be a volume change less than the volume change in the regular piston. So if we use the formula work equals PV, Mr. Riley's actuator would have the same pressure, he would have a lesser volume, but he actually generates more work because he overpowers the conventional piston. So the formula work equals pressure times volume change, which applies to the conventional piston, cannot apply to Mr. Riley's actuator. Just because you have a lesser volume, you have an equal pressure, and yet Mr. Riley's, by that formula, should in fact have less work, but in fact he actually has more work. Okay, now we'll have another demonstration for you that we will show you with respect to two pistons opposing each other. Now, keep in mind that the scientists said that the pressure advantage or the efficiency advantage is 15 to 70% for a conventional piston. This next demonstration will show you that we only need part of that 15% efficiency advantage to actually have one piston overcome another one and push fluid out of it. Okay, this apparatus is set up to allow us to demonstrate what the impact would be of a differential in efficiency of 15% with respect to one actuator to another. Now, the reason we have the 15% is the minimum efficiency differential reported by all the engineers and scientists who have tested this. The lowest value they've attributed to the diamond-shaped actuator is 15%. So 15% efficiency advantage would mean that it would generate 15% more power given the same quantity of fluid at the same pressure. Now, to have two identical actuators like this, what you can have in order to make this actuator 1 15% more powerful than actuator 2, there are a couple of options. We could increase the size of this boundary phase here by 15%, or we could actually increase its pressure by 15%, or decrease actuator 2's pressure by 15%. Or what we could do is we could replace actuator 1 with a diamond-shaped actuator, which would have 15% higher efficiency advantage, so consequently with the same volume change of what would be in actuator 2, actuator 1 would express a force advantage of 15%. Now what we've done in this case is we've had controls set up to measure the differential in pressure between the two actuators, and what we do is we demand a particular value of differential we have here on this gauge with this switch, and then it'll read up to match on this gauge, which will lessen the pressure in actuator 2 and leave the actuator 1 pressure the same. So we have 70 pounds pressure on this gauge, which is associated with actuator 1, and 70 pounds pressure associated with actuator 2. What happens when I demand a differential of say 4.5 psi, what will happen is actuator 1's pressure will drop while actuator 2's pressure maintains the same. Now what we have is push buttons here, pneumatic push buttons. This gauge is at 0 now at the moment, and what will happen is as the actuator 1 starts to overpower actuator 2, you'll see that this gauge will jump up to 20 pounds once this push button is being relieved by this linkage. Once it gets all the way over to the other push button, which is associated with actuator 2, then the gauge there will jump up. Now I'll dial in 4.5 pounds pressure differential. Now 4.5 pounds pressure differential based on 70 pounds is less than half of what's available to us with respect to energy efficiency or power efficiency on the diamond-shaped actuator. Now you'll take a second for the controls to catch up. You hear it start to whine in a second, and you'll see this pressure start to drop as soon as the control bleeds off. It's starting now. You see this gauge dropping, but watch the gauge on the push button, and what you'll see is it will, now we've gone up to 4.5. Now this gauge here is indicating that we've achieved the 4.5 differential. This gauge just jumped up, so it's telling us that the linkage moves, and in fact you can see the linkage moving in this direction toward actuator 2. What that means is with a differential of 4.5 pounds, you will have actuator 1 overpower actuator 2. Now from the efficiency advantage with respect to the diamond-shaped actuator, if it was a 70 psi with 15% differential, efficiency differential, then we have available to us 10.5 pounds differential to still prove our point. We're only using a 4.5 pound differential instead of the 10.5. So now you see it, the second gauge jumped up, means we hit this push button, so it drove from this push button to this push button. I'm going to dial this back to 0 again. The gauge will come back up to 70 psi on both, and you'll have seen a demonstration whereby with a 17% advantage in efficiency, or sorry, 15% advantage in efficiency on a diamond-shaped actuator in this situation would be able to overpower the second conventional actuator, actuator 2, and he would only require less than half of his 17% advantage in order to push fluid out of the second actuator, and he would in fact, in the device that we've created, the diamond-shaped actuator, which would replace actuator 1, would push fluid out of actuator 2 in a volume that he could feed himself, and he would actually feed himself his own total force or own total volume of fluid while using only half of his potential advantage. So there'd be an advantage of more than 15% of the efficiency differential left over for external work. Okay, now we'll show you another demonstration with respect to Mr. Riley's actuator with the exposure of the diaphragms within them. Okay, with this demonstration, what we're trying to illustrate is that the side walls of Mr. Riley's actuator in fact do exert a force So the two sidewalls here and the sidewall there exert a force supplementing the top force of the actuator. So it's similar to the little man A would be pushing the top from the demonstration before, little man B and little man C. What right now we're doing is we've pressurized it at 7 inches water gauge. It's driven out on the fish scales. What happens is it drives forward, the shaft pulls on the scales go. So I'll take air off of this unit now, and you'll see it retracting backwards. So the scale's going back. There's a spring in the scale which is causing this to be pulled back. Now we'll let it go back all the way to where it will. Now it's stopped at about 8 pounds on the scale, even though we're at 0 inches water gauge because of the friction within the unit. We'll use that as a common base for the comparison to the one with just 2 walls. This particular actuator has pressure being exerted on all 3 walls. What we'll do is we'll increase the pressure, and this again is in inches of water gauge. So it's 0 to 8 inches water gauge. 1 pound per square inch is 27.71 inches water gauge. So what we'll do is we'll take the pressure up, and you see the scale starting to move. We're at 20 inches water gauge there now. The scales are going past almost up to 24 now. We'll go to a common point, 32 pounds on this as a comparison between the next model we'll show you. Now you're at 32 right there, and you're at 28 inches water gauge, so very close to 1 psi to do that. So with this particular system model we see here, the diaphragm is still not quite touching the top in every part, but it's most of it. And so what's happening now is we have a force on the top plate and 2 forces on 2 outside walls requiring only 28 inches water gauge pressure to drive it scales to 32 pounds of total force. Now what we'll do is we'll take the diaphragm out of this model now and replace it with another diaphragm which will not be capable of touching the top plate. It'll only touch the 2 outside ones, and we'll see the performance relative to this one at that point. We've changed the diaphragm in this model. It's the exact same model, just the diaphragm, as you can see, is not able to touch the top plate. So consequently, the pressure of the diaphragm is touching the sidewall this side and the sidewall on that side, but not the top. Now we've got it at 80 or 76 inch water gauge pressure there now. We'll drop it back, and you'll see the scales will pull back as it did before, the spring in there, and the diaphragm will collapse. And we're back down to 8 pounds as a start point again because of the friction within the unit. But we're just to come to a common factor now. So what I'll do is I will increase the pressure on the device by a gradual switch which I have on my hand, and you'll see the scale starting to move. Now what we'll do initially is take it to 28 inches water gauge, and you'll see that we're at about 14 pounds on the scales, where at 28 inches water gauge the diaphragm, when it could touch the whole thing, was driven to 32 pounds. So we'll increase the pressure we'll go to 56 inches water gauge, and we'll watch the scale. We're at 56 inches water gauge there now, and we're at about 26 pounds of force. We'll have to get us up to 32, we'll increase the pressure a bit more. At 60 inches water gauge, and we're exceeding the 32 now. So at about 60 inches water gauge, we were able to drive the scales to 32 pounds, which was the equivalent force that we were able to do with the full diaphragm touching the top plate. We're getting to 32 pounds with 28 inches water gauge rather than 60. So there's more than 100% more pressure required when the 2 sidewalls do not have the assistance of the top plate. Now we've had it contested through scientists that the sidewalls do not actually add force to the top plate. The reason we say that is what they've said: if the top plate is equal in area to that of a conventional piston, and the volume change is the same at each, you do the same amount of work, which means that the force through the same distance would be equal for both types of actuators. In fact, the regular piston would have a force equivalent to the top plate of Mr. Riley's. So you'd have work would be equal to force times distance, or displacement, you would have on Mr. Riley's, then you would have not just the one force of the top plate, you have the force of the top plate plus the two side plates. And this demonstration demonstrates very clearly that the two side walls, in fact, do provide a surplus force to the top of it. Now, we have a serious situation with respect to energy and pollution on the planet. This device, we know, is not the only solution by any means, but we believe it could be a contributing factor for the probable survival of the future generations on the planet with a clean source of energy with no pollution. Now, we know that we are contesting one of the fundamental laws of physics, which is saying that energy is preserved. Energy can't be created or destroyed, but only change form. The people creating that physical law back centuries ago, in my opinion, were a touch on the overly confident side. If you were to declare something to be completely impossible with respect to energy, which they did, then that would be implying that you knew everything about energy that ever had been done on energy. You would also know everything with respect to energy that existed at the time, and you'd also know everything about energy which would be known in the future. That's pretty confident. All I think a person can say from a scientific point is that they don't know how to achieve something. They know of no one else who can achieve it, but that doesn't mean that no one in the future will be able to. Now, we also have a situation where the definition of energy is a problem. I haven't seen one statement by a scientist yet that actually describes what energy actually is. They say what it does, but they don't know what it is. It's like gravity. We don't know what it is. We can only describe what it does. So again, I think it's a tad on the overconfident side for someone to set definition with respect to what something can or can't do when you don't even know what it is. So if we pull together as a team, everybody in every field, I'm sure everybody's got something to contribute toward cleaning up the environment and helping the probability of the children of the future living a better life. I think we should all pull together. We are quite willing to share this technology with virtually anyone who wants to use it, and all of our research will be available to them. We have problems currently with the diaphragms breaking on us quite regularly, and so we need assistance with respect to the seals so that we could finally have hydraulic devices which don't require the diaphragms, just total seals, or good diaphragms which will not break on us. So as a collective effort, as parents, grandparents, we all should pull together to do the best effort we can. Thank you very much.